we can put a mixture distribution on them and say, well, we think actually the sample we've got is from two different populations of people who have different distributions of the regression coefficients or partlets. And we could do that. Here, this is just basically a linear regression model, but it's an additional layer. We'll call it an additional layer. So those z's, those are covariates of the regression coefficients, right? The beta. And the psi's are regression coefficients from regressing the betas on the z. Okay. So when we do these things in R, there's a bunch of things that are already in there that you can use. There's a package written by a colleague of mine, Peter Rossi, called Bayesian. I'm going to show you some results from one of his algorithms in a minute. Choice modeler is a little bit more recent. It actually calls the same routines that Peter's routine calls. Then you can actually, without much difficulty, right, in the specific package language of these different packages you can call, do the same kind of estimation. One of the things that's different, for example, in the bugs language is a declarative language. It's not a procedural language. So you write things as if they aren't loops, but it doesn't actually execute the loops. It just knows that that's what the embedded nature of the different parameters are in the distribution. RStan uses different samplers. It uses the Hamiltonian. It used to be the hybrid Markov chain, kind of gets you the same place. It also has nuts in there. I don't know if you've noticed that. The no U-term sampler that they call it. They actually all have their own idiosyncrasies. So sometimes when you're doing these models for real, you might use really different simulators to see what you get. And JAGS is another Gibbs sampler. So those things, along with all the other tools that I mentioned previously, give you a pretty substantial arsenal for doing these things. You just need to have time. Okay. Finally, so we're getting down to the bottom of the hour, I'll just spend a few minutes kind of giving you a flavor of a particular application using these techniques to model the structure of preferences. So these are data from a study that's slightly disguised, a few years old, that had to do with the design of tablets like iPads. And it was for a company that was in the business of consumer electronics, didn't have this kind of product in the market. And they wanted to understand what the important determinants of preferences were for tablets of certain configurations. So they did, in their case, fortunately did reasonably good previous research that involved a lot of qualitative work and secondary research looking at the market, and talking to people in groups, and visiting people as they use their tablets, and tried to sort out the various characteristics they thought were the key determinants of what people would prefer when they were thinking about buying a tablet. And so what all that resulted in was a choice design that had 36 choice sets with 3 alternatives each. If you think back to that thing about the yours that had 3 choice sets, there were like 36 of these that described tablets in these characteristics. The attributes were how much RAM did they have. There were 3 levels. There was 8, 16, and 32. Screen size 7-inch, 5-inch, 7-inch, and this sort of mini tablet, right? 5-inch, 7-inch, and 10 inches. Processor speed, can't remember what they were, but there were 3 levels. Maybe 1.62 and 2.5 or something like that. Gigahertz. 3 levels of price, $199, $299, $399, and 4 brand names, which I'm not going to mention. And so this design was constructed actually using an algorithmic procedure. So it was a reasonably good compromise between the precision of the estimates and not having too long a task. And it also allowed it to estimate coefficients for certain interaction components. And in particular, they were interested in brand by a price component interaction because their theory was, or what they were guessing, is that price sensitivity would vary by brand. And that's often the case, one would think. And it might be related to other things. So there was additional data that was collected. This was done online, and an online survey. And so that's what the data were like. So these results, actually, they were analyzed in a bunch of different ways. I actually have some students doing this right now, this way. One way that the data has been analyzed, and the way they're doing it, is to use this particular procedure out of Peter's Bayesian package called PUL, using static all, higher MNLDP from this package. And what this is a hierarchical multi-nomial logit model with a drill-shaped process prior on the multivariate distribution of the data. And that's purely a pragmatic variation on this. And the reason is that what many have observed over time is multi-nomial logit models with multivariate normal distributions on regression coefficients tend to have tails that are really thin. So the drill-shaped process prior is actually a way of basically saying, well, we actually might have a mixture of people with tails of different things. And we can actually estimate dynamically through the iterations how many of those components there might be. And in fact, that's how you go about doing non-parametric mixture models using Bayesian techniques. And it's just sort of in there. Sometimes you can see the difference in sometimes you don't. But in this particular example, that's kind of the technique. What's smart about it, actually, if it doesn't need to add components, it doesn't do it over iteration. But you can see the progress as you go through the chains, because for every iteration of the algorithm, you can see the components that are being added or not added. It's kind of a nice thing. 30,000 simulation runs, thinned every fifth. These kinds of models, typically these multinomial logic models, you need a lot of iterations compared to something simple like a Gibbs with just multi-rate normal distributions. We've thinned throughout the first 5,000. That left us 1,000, which really corresponded to 5,000 iterations out of 30. And of interest in particular for marketing purposes would be things that have to do with the distributions of the betas and the deltas, and I'll tell you what those are in a minute. Both the deltas are the beta covariance. Remember that model I showed you that there's the size that actually related to beta sub i's to the z's. That should have been size there. I messed up when I did select. And so here's kind of a very small piece of what the results look like. And then I'll point out a few things that actually will illustrate the kind of inference that we would do and how you use these results at the end. So up at the top, basically, is kind of how it is. This particular procedure is called Narc. And it's basically in R, every result is basically an object. You have to assign it to something, otherwise you're just going to fill your console screen and you won't have anything left. Everything in R is an object, right, pretty much. And basically, it's the arguments that it's calling here. These are required. Data 2 is actually a list of data lists. So it's a data structure in R that's organized by respondent and by their choice responses and the design matrix. And this MCMC thing actually here is another list, and it just specifies how many iterations we're doing and we do things like that. So you run this actually on a laptop, like a modest one, well, maybe one of our Macro Pros. It might be a 20-minute run to do this. And it's running in an optimizer in C, but there's a lot going on here, right? So my advice to students is, if that's what you're doing, go get a beverage of your choice, because and save it for sure when it's done. Save it. And so what this returns is what a lot of the routines in R returns. It returns a list, a list of data objects of results. And in there are things like, these are the beta draws are actually a three-dimensional array that's basically, it's 360 by 14, there's 14 regression beta coefficients in this model, by 6,000 when it comes back. Remember, we're going to throw out the first 5, right? And delta draw is actually that, it's the delta I mentioned before that should have been on the side. But those are the draws, the chains for the coefficients from regressing the beta sub i's on a couple different covariants that actually in this case happen to be previous ownership experience indicator and indicator for whether the respondent is seeing it or not. And then a variety of others. Here's a chain for the model 1 likelihood. Right. So all of this is coming back, they're all chains of various kinds, and they describe things like the Dirle-shaped process mixture and so on. So all this is actually, this is kind of what I said, results overload. You really got to know what's important here, otherwise you're going to spend a lot of time looking at all sorts of things that are interesting that are not going to help you answer some kind of decision. But anyway, here's the chain for the 1 likelihood, right? And you can see basically starting from some very negative value, and it goes up and it's pretty flat. This is the chain for the 3rd regression coefficient for the tensor respondent. And here again, this looks like, it looks pretty good. Lots of dots. But 6,000 samples. That's thin from 30,000. And we're going to use, in a minute, I'm going to show you kind of some summaries of this for inference purposes that are in the last step. So I mentioned earlier the kind of the sniff test, right? And one thing we like to look at initially is that, at some aggregate levels, everything looks like it makes sense, or things look backwards. What do we know about this? Well, I've labeled, these are the means over respondents in the last 1,000 draws. So we're taking the means for each regression coefficient for the last 1,000 draws across all 360 respondents. Now, these respondents are all probably from the same universe. So there should be some similarity between them in terms of what the regression coefficients are. We should sort of see some overall patterns that make sense. And one is that we know that This is the effects coding value for whatever the middle level of RAM was. And this is this middle one, that's highest. And so it's always a emitted level because we've effects coded here, but we can figure that out by derivation. We know that it has to be negative for the sum of these two. So we can actually get that out as a full part order. Well, what makes sense here is this. Look, actually that the largest regression coefficient, it has the largest value. We'd expect that the larger the amount of RAM, the more positively it should affect overall preferences. So that kind of makes sense. Screen size, same thing here. Remember, there's a missing one here. This one will be negative. Because these are all effects coded, so they're kind of gives the test. Midpoint largest. CPU speed, low, medium, and high. Price actually. Now price should be just the opposite, right? Remember, there's a lowest price level that was the reference level. Here's the mid price level. This would be what did I say it was? $299, $399. So you can see that generally speaking, these kind of things make sense. Now these are kind of so aggregate we would never use these unless we were forced to support decision making. But now we can actually do the same thing and look at selected percentiles that describe the densities for individual respondents now. So here's respondent 4. And we're looking at the 50th, and 95th percentile of responding 4's 14 regression coefficient. This respondent 4's beta sub i's. And these are, we could actually make the graphs, the density if we wanted to, but we can look at these as a summary and basically say, well, do any of these look like they're different from 0? And let's see, well, if we look through here, wow, that one doesn't. This one looks like that density is below 0. Look, the 95th percentile is negative, right? So if we were to look at that picture, we would say, yeah, well, that one's different from 0, most likely. Right? Remember, these are random variables, so there's no true unique value in a population. They have uncertainty around them, and this describes their uncertainty.
So it's a way to interpret that from the data that's up there, that the CPU speed, I guess it's speed, is the most important element that people are looking at, followed by, I guess, maybe price, or maybe, let's see, no, maybe it's the amount of RAM.
Yeah.
Would that be an appropriate method of thinking about those results?
Yeah, with a caveat. In fact, a traditional method, it's kind of a legacy method, there's actually a specific quantitative metric called attribute importance. And an attribute importance is the percentage of the overall range and all of the attribute levels hard worse. So it's like a percentage out of 1,000. Why it has to be considered with a grain of salt is it depends on the attribute levels you're using. So if we had a different level of RAM, because right now we're not seeing specific,
right,
that would change. It could change. But generally speaking,
but given the data, that would be the.
That's right.
Yeah.
Given these specific values, the specific experimental conditions that we use. Yeah, that's right. And here all we're doing is saying these are just means, but now for this particular respondent, we can describe and summarize the densities, the distributions, the posterior distribution of every one of those regression coefficients. So now what we have, getting back to this sort of results overload, actually what we have is this represents kind of the interesting problem in post-processing data analysis. And it's really, what's happened, the way I think about it is, we run these algorithms, the model looks like it's performing adequately, now we've got like this whole new complex data set to look at. And now we can start describing it in different ways and using it for making inferences. So I'm running over, I'm going to finish in a second. All right. So we can ask questions like, for that respondents, is there likely to be a difference between the price level data, regression coefficient? That's actually pretty easy to do because we just difference those chains and look at the distribution and describe it. And then the question would be, well, how different is it from 0? It doesn't look too different from that. So I wouldn't say, it's not really that likely. Using this kind of analysis of the posteriors. No t-tests, no asymptotics, no p-values. Just look at that. In fact, here what I've done is I've used this as a function, built-in function called empirical CDF. And I've actually said, define the function and then tell me what the percentile is of 0 in that distribution, the difference distribution. About 18%. So 18% of that, of the density is below 0. And I would say, yeah, I don't think it's really that likely. There's something there, but you don't kind of get around that problem of figuring out like how big is big, but you actually get a much richer picture. Okay. And finally, I mentioned that there are these beta covariates that I've given different group names to at different times. And so basically what we have here is, here's the summary of those what I call them there, the delta coefficients or the size. These are the regression coefficients from regressing the beta sub i's on the indicators for prior ownership and for female. And you can look at these things in the same way. I could make graphs here, but it's actually kind of a nice way to start just looking at the percentiles. I know what the median is. I know the 5% part what the location is of the 5th percentile and 95th. And I can go through and do the same analysis.
This may be kind of pedestrian. One of the things that would be very helpful is if you just replace the 3-digit precision numbers with colors.
Absolutely.
Then you can just glance at it.
Yeah. And
rather than having to like scan it.
Given the amount of results, actually this really lends itself to data visualization. And then the question is, how do you describe these things? But that's exactly right. So.
Sorry, it's off topic.
No. No, I mean, it speaks to this point of this is you have a lot of results, and then figure, these are the kind of results that, we might look at when we get the initial results of a run and we think is satisfactory, and we're looking at things we might want to represent in other ways. So we present them differently to like management decision-making ways. In fact, there's a lot of this uncertainty we probably wouldn't represent, but that would tell us about what it is we're likely to claim is important to look at. But my point here is just simply to say that every single one of these now has a posterior density that we can describe, and we can use that for making.
Don't think too much about how color relates to cumulative density function.
I don't know, but I think we need a widget for this. Okay? So anyway, in a nutshell, what this stuff is used for is for product design decisions. Sometimes it's used for things like trying to figure out what messaging should be going in ads. These results will actually oftentimes be put into some kind of simulator that decision makers use for doing what-if analysis and occasionally for optimization. Those are really hard problems, especially since you need to take into account all the differences. To do it properly, you have to do what's called full enumeration. So you have to use all the information from all the respondents and figure out kind of what would be the single best configuration given all of their individual differences and preferences. So that's actually kind of an application of this sort of modeling procedure done in R, using techniques that are already in there, and what it is that's used. So, and that's my story, and I'm sticking to it.
You referred to John Cushy. I happened to pick up his most recent book, which is all R-based.
Oh yeah. Nice cover.
Oh.
Lightweight.
And so I'm happy to stick around, and I know it's Friday, but do you have questions? Or?
So in the successive layers of these hyperparameters and so forth, I'm trying to understand when you're doing these sort of synthetic sampling. And I guess I've been confused recently by looking at neural networks and deep learning.
They're also
I'm confused by that.
to some degree.
Where those things basically that different layers recognize they're not dependent on one another in a sense. But if you've got samples and then you're looking at hyperparameters or some sort of characterization of the stage before, and each stage is subsequent. I mean, it's hard to imagine that there is still dimensionality that persists through those depths.
Yeah, that's a good point. And actually, I can kind of give you an
It's not
anecdote.
just reducing to like some single parameter somehow after multiple stages.
No. The trick behind all this is that estimates become conditionally independent of other things, depending on how you draw the model. There's graphical representation of these things in directed acyclic graphs, where it's plates that are actually used to describe the relationship, describe the interdependency of things. And so, not all parameters are independent of everything else. They're conditionally independent of some things, depending on the nature of the dependence relationships in that kind of graph. But you can't, there are, we don't know of any theory, like smarter people than I that I've talked to about this, don't know of any theory that tells us at some point what constitutes over-parameterization, right? Because if you first look at this, you say, well, yeah, sample of 360, you need thousands and thousands of parameters. But There are cases where we found that like more complicated models that should make sense that allow for more heterogeneity don't do any better than models that don't. And one sort of pseudo theory that we've got is actually there's just no more information left in the data. You know, it's just not there anymore, to your point. And you know, that can sort of happen. It's like we've exhausted it all in this parameterization.
That's exactly, I mean, you know, I came out of, I know he's interested in stock market modeling as it's film in the back, but part of the problem is that so much of the stock market modeling is trying to torture a very small set of numbers that is in fact being influenced by completely outside factors. So no matter how precise you can get the modeling of the time series, it's useless because you're being impacted by outside
Sure. So
factors. And so you've got a fundamental problem of your model construction to begin with.
Yeah, that's in the specification.
Yeah.
We also see that in areas like marketing mix modeling, right?
But at least
There's always something outside, and the best you can hope for is it's more solid. Because otherwise, you know, you have great difficulty in marketing mix modeling and things like causal inference, because you can see relationships, but you can't satisfy the requirements for valid causal inference, and you may well be seeing things that result from limited variables or other problems or causing things to be designed.
Yeah.
You know?
And back to the market example, which we've talked about, is you can analyze the historical market all you want. That doesn't tell you anything because the world within it, which it exists, is not the same world.
people also don't know what they really want.
Well, what's that do?
Sure. Well, that's one argument that's made for these techniques, is you don't ask them, you just make them choose between things. And so, it's not infallible, because what happens with these techniques, there's a whole lot that happens between when you do these measures and when something gets into the market. And, you know, one thing that's actually generally referred to is from an industry perspective, the post-launch new product success hasn't changed for decades. It's between 1 out of 5 and 1 out of 10. So despite all our fancy stuff, like a friend of mine in Maryland says, you know, every time they get papers they review in journals like marketing science or quantitative marketing economics, everyone basically says this is so much better than all previous models. He says, by now we should understand everything. Consumers, we don't do any better. You know? So because things change. Right?
Another very interesting component of that is are you familiar with Nicholas Tille's book and works? I mean, you know, his whole theory about the black swans and the pattern, because for so many of what we're trying to model is there's unknown fatter tails that are not taken into account. And that, of course, causes big eruptions in markets.
Sure. Yeah, well, you know, in the area of complexity science, they deal with different sorts of distributions. We deal with kind of sort of symmetric things. They deal with things like power loss, right, and things that exist at infinite scales. And like in the black swan case, it's something that's this really, really rare, really big event.
Yes.
But actually, maybe we've never observed one. It's kind of a black swan event,
right,
because nobody went to Australia to see them, right? Or they're so rare, like the big one that went to California, right? So their guesses are really bad at best of these things. Because we have a lot of evidence, but they kind of exist on, they're kind of scale-free thing. Yeah. Anyway, all right. Well, thank you very much. I appreciate it.
Thank you.
I was going to ask whether we want to do, last time we were talking about an interesting project. I got 2 candidates. Do you guys want to hear it?
Yes.
One is matching medical records, and another one is analyzing Twitter data.
What is it?
Yeah.
I'm more interested in medical data.
Oh, medical data.